All right, welcome back to week 9 of SC0X. This week, we're going to talk about regression and simulation. But before I get into it, let's step back and think where we've come in this course. Because this course was really all about developing 3 types of analytical models, tools that you can use later on in your career as well as for future courses. So we started off talking about optimization for the first 4 weeks. And so we really focused on prescriptive models, models that give a prescription for the future. It tells you an answer. It tells you you should do this. X should be 3 to be optimal. And that's what optimization was all about, building prescriptive models. So then we want to turn now into different types of models. And we're going to focus on prediction models, models that can be predictive and tell you what probably will happen, as well as descriptive models, models that describe the current situation. And if you change something, describe what would happen. So for prediction models, that's really what we're going to talk about for regression. And simulation is more of a descriptive method. And so the important thing is that these 2 methods are not, prescriptive models. Neither regression nor simulation will tell you exactly what to do. They will tell you, given these things, here's what will happen. It'll either predict what will happen and be a predictive model, or it will describe the situation, describe what will happen. So it's an important thing, and it's kind of the way to clarify the difference between optimization and simulation and regression. So let's start with regression. So we finished up the last lesson talking about multiple random variables. And what if we have the case where I have a variable y, but it's a function of some variable x? And let's say that x here is the square feet or the area of your store, and y is the sales, the revenue. And so we think there might be some kind of relationship. As my store gets bigger, I can have more stuff on the shelves, I might be able to sell more. And so I can go out and I can sample a bunch of stores, and I can plot this. And let's say it looks something like this. Right? So what we're going to do with regression is we're going to find the best fit line that maps that data. And so we're going to come up with something that looks something like this, a best fit line, and we'll describe the method by which we find that line to minimize the sum of the squares of the errors, essentially the distance between here, a best fit. And we're making a big assumption on this functional form. We're going to say it's going to look something like B0 plus B1 times x, where B0 or beta naught is the intercept, right? And beta 1 is the slope, where that's 1 and this would be beta 1, the rise over the run. So what we're describing is a linear equation. And that's what we're going to do with regression. We're going to focus in on collecting this data and being able to come up with a linear relationship that describes that. And we'll come up with an equation, because I can use this equation to try a different area and be able to predict what the sales would be. So we'll spend a lot of time developing these models, talking about different functional forms we can use, and we'll talk about a couple other things. One is the goodness of fit. How well does my equation fit the line? Is it good enough? And then we'll also spend a lot of time focused on these coefficients, these parameters, and we'll do a bunch of tests for significance. And hopefully that word means something to you now after the last week, and we'll look specifically a lot of times at the p-value. And we'll talk more about that. This is why you learned it in last week's lesson, to apply it here. After regression, we'll turn our way over to simulation. And simulation's interesting, because this is the way where you can model or come up with some insights on a system that's overly complex. And sometimes even the simplest system can be very complex. So let's look at this simple situation where you're here, you run a store, and your job is to know how much stuff to have in your store, how much inventory to hold. Right? So that's what your problem is. You're facing some kind of demand. People come in, but they don't come in always when you need them. They come in randomly. That's a random variable. And let's say it's distributed normally, I don't know, with some mean and some standard deviation. So you don't know when they're going to come. And even worse than that, you don't know when your supply is going to get here. Because let's say you're selling fish. And the fish, you don't know how much you're going to get each day. And so this could be distributed some way, and we don't even know what the distribution is. We might just have a bunch of samples, and I have a bunch of parameters there. It might be an empirical distribution that we talked about previously. And the question is, how do I figure out how much inventory to hold? Now, if these are well formed, then this would be a very easy analytical solution. I could solve this. But in many cases, you can't. And so what you do is you simulate. You set up a situation where I'm going to have a series of days, 1, 2, 3, 4, so forth. And every day you have a random selection of demand that comes. You pull from that random sample. This should be sounding familiar from previous week's lessons. And I come up with an instance of that demand. So I'm randomly sampling that, and I'm simulating what the demand would be. And what I want to do is put in a policy here and see how well it does. So I run this for a year, and I see how much money I make or I lose. I can repeat this over and over again with different policies. What if I hold 7 in stock? What if I hold 9 in stock? And it's a way of testing different policies and see how well they do. Because remember, this is descriptive. It's not going to tell you what the right number is. We'll talk in other courses about how to come up with an optimal solution with this, but if it's overly complex, there's no closed form analytical solution that will give that to you. So simulation is very strong and very widely used with complex situations that you can't capture totally analytically. And it's a way of testing different policies. But again, it's a descriptive model. It'll describe the situation given the underlying inputs. It won't recommend a solution. All right, so we'll talk about regression. We'll talk about simulation. Hopefully you'll see how they can fit together, and these are 2 other tools in your tool belt you can use for your analytical problem solving. So please try the quick questions, do the practice problems, have fun.